Ramadi,
and we will share with you our journey in this year's Untitled Chapter. Similar to last year, there were many hurdles and obstacles that we had to overcome, not just about robotics, but about how our team endured these trying times.
in this video, we'll talk about our various mechanisms, such as our intake and cradle. We'll also be talking about our programming side, specifically our team code. Finally, to wrap it up, we'll be talking about our driver control enhancements.
On the robot, we have four primary mechanisms: the intake, the spin wheel, the cradle, and the grasper. Our intake is 3D printed and run by a 1500 4:1 X motor, as you can see here. Also, we have three primary axles that go through the 3D printed intake, which function to carry the game element up into the intake and then sort of drops it into the cradle. After securing the game element with a gate, it stretches out in the other direction and allows us to quickly back up and drop off game elements onto the highest level of the shipping hill.
For next week's competition, we have decided to make another iteration for the intake. This mechanism is a mashup between the cradle and the intake, as shown here. It is smaller than the last intake, so we don't allow more than one free. This is then raised by an AnyMark motor to place the shipping hub element on any level similar to the cradle. This is better as a more simple design allows us to have no more maintenance. Here's a demo of the cycle. The second change we made is to have two spinning Gecko wheels to rotate the carousel, because we needed to be prepared for coming in at any angle.
Another one of our unique designs was our prize drivetrain. We wanted to create a drivetrain that could fit through the barrier gap of 13 inches, as we wanted to make our shipment cycle faster. To accomplish this task, our team decided to offset our Nevers 20:1 motors to create a slim design that could meet our complex requirements. However, due to our unorthodox offset approach, we had to utilize a 1-to-1 gear ratio to ensure our wheels weren't offset the way our motors were. We utilized a touch sensor on the cradle in order to create a sensor-based stop. This is more reliable and safe than a mechanical stop and saves more time compared to a time-based stop. The sensor also protects the cradle from violently shaking and undergoing the risk of falling apart.
An important part of our co-design was the implementation of state machines. The robot in our program that we direct is made up of many components, which all have their own classes and functions. These components also have their own state machines, such as lifter idle or lifter is lifted. This lets us know what is happening to each component at any given time in the program, which is very useful in our teleop. By using state machines, our code is organized and easier to share with others. One of the most important additions to our robot this season was PID and the IMU. The motor encoders attached to the drivetrain motors allow us to keep track of the rotation the motor has made. To add to this, a crucial element in our autonomous code is the IMU, or Inertial Measurement Unit in the expansion mode. We use the IMU for both driving straight and turning in autonomous. With the IMU and encoders, we get a feedback loop of the heading of our robot, meaning that if it's veering off course, we can use the heading to correct the angle. To use this, we reuse our award-winning PID algorithm that we learned from FLL as a template for us to recreate in the robot this year. The algorithm uses a proportional value to dynamically adjust the error in the motors, minimizing the heading. Because of components like the IMU and motor encoders, we are able to make our autonomous repeatable and accurate.
To summarize this video, our robot has many unique and different aspects. The intake is 3D printed and uses AnyMark spin takes. The cradle is another 3D printed lightweight mechanism that holds heavy blocks and balls to drop off the highest level. Our drivetrain, the most challenging and unique part of our robot, consists of offset motors and 80-tooth gears, both of which are uncommon in FTC drivetrains.
We use our code in PID and IMU'd in order to help the drivers in their run. This is another great season of learning and experience to use in the future. Thank you for listening.